So last time we stopped at the sound frequency. Okay, and then we have, just draw it this way. Okay, omega 1 and omega 2, they sum together to generate omega 3. So the nonlinear equation for this becomes I think last time we stopped here. And apparently there's a phase matching condition show up here. The phase matching is K3 minus K1, K2. Okay? It makes sense because you have two photons of lower frequency, they combine generate a photon at higher frequency. So this is energy conservation, but also you need momentum conservation. So K1, K2, if K1 plus K2 equals K3, this is the phase matching condition. Okay. So in general, this would be difficult to solve. So if it's not phase matched, okay. So in this class, we just simplify things. Okay, we explain how we achieve phase matching previously. So we assume that we are able to do that. Okay, so we assume this for the rest of the calculation. Okay, and the second thing we want to know, we want to set some constraint to our system, is that we want to have E2 much larger than E1. So E2 is like a pump, right? E1 is the one that carries a signal, okay? And then E2 is like a pump, help it to convert to E3. So in this sense, this would be also. Okay. And when we have this condition, we know that if E2 is very large, much larger than this two, then this dynamic equation, okay, these two terms doesn't affect much of E1. Okay. There'll be a little bit, you will convert a little bit of photon from E2 to E3, but those photons are the number of those photons are very small, so you can assume E2 is a constant when your photon is propagating. It's just the same as the as what we have done for the second harmonic generation. Okay, now let's briefly think about the behavior of E1 and E3 before start solving this equation. And now we know it's phase matched. Okay, phase matched. So question 1 is, well, we want to generate E3. Assume perfect phase matching condition. Will E3 keep growing? Well, it's still much smaller than E2, but under that limit, will it keep growing with the propagation distance? Show of hand, how many of you agree it keep growing? How many of you disagree? Okay, the rest of you are not in the class, or okay. So let's think again. U1, okay. U1 increase or decrease? Decrease, right? Because you need the U1 to generate E3, right? So decrease. Will it decrease all the way to 0? No? Or maybe? So let's just assume it goes to 0, okay? Maybe not constant rate, maybe like this, right? Because when you have less E1, then your conversion efficiency to E3 become much slower. So it will not be linear, of course, but let's just assume it goes to 0. Now, if it goes to 0, can your E3 grow? No, right? You need a photon of E1. So E3 must stop somewhere. Okay, let's see, just stop here. And let's put the crystal here. CZ. Okay. And yes.
At some point, would you get photons at E3 converting back to E1? So
yeah, that's where we're going. Okay. Yes. So so you can see from here, if we arrive at Z0, this point, if there's a point like this, then what will happen is you kind of switch your input and output, right? Your input used to be E1, and your E3 is 0. And then you say you are able to convert it to E3, right? Now it's like your E1 is 0, but you have a E3, right? So it should going backwards, okay? And you can keep doing this. So without solving this equation, you should know that the answer is the oscillation. Okay, the answer is oscillation. Now let's look at it. So we only need to consider this one and this one. All right. Yeah, E2 is much larger. Yeah. And we also say phase matching condition, so this one is 0. Now let's do this. We'll have okay. Okay, this is the first one. E2 is a constant. And then by the way, the other thing I want to ask is, if we merge these two figures, okay, let's say we merge these two figures, and then let's say we plot a new figure here. Okay, we start with the power of E1 is P1, and then we know it probably goes down like this. Okay, and then the power of P3 will increase, right? Okay, now the question is, the maximum power of P3, is it higher than P1 or lower than P1, or equal to P1?
Higher.
Why?
You're getting power from the pump.
Correct, yep. So the other way to think about it is that in this process, the photon is actually the number of photons disappear in E1 is the number of photons you create in E3, and E3 its frequency is higher, so the energy per photon is higher for E3 compared with E1. Okay, so without much calculation, you can actually know how much increase you get. Okay. So let's. Okay, so this is a standard coupled mode equation, or coupled equation. You have E1 here, and then E3 here, E3 here, E1 here. Okay, and then there's a coefficient in front. And the way to solve this equation is kind of standard. But let's simplify things a little bit. Let's assume it's K1. Okay, we don't want to carry all these things through our calculation. Okay, the way to solve this is, again, you do a derivative on, let's see, which one do we want? We actually want, you can do both. Well, I guess it doesn't matter. So let's do it on E1 first. Okay, so what you can do is you can do a derivative of Z on the entire equation. Okay, and what this gives you is K1 right? And now you can substitute partial E3 partial Z using this equation. And you get K1 times K3 E1Z. Okay. And let's say K1 times K3 is a minus number. Okay. So you get K1, K3, you get Right, this is a positive number. So you can define a real number square. Okay. Usually in this second derivative equation, you always want to have a square term here. Right? Otherwise, in your calculation, you'll have a square root in your equation. I think this is enough space. We can solve this. And oh, there's a minus sign, right? Yep. Okay. Yeah, there's a minus sign here. Okay. So the solution is actually obvious. Right? It's sine and cosine. Right? If you do sine, one derivative becomes cosine, and then the other derivative comes back to sine, and then you acquire a minus sign. Okay, so the solution is, well, actually, let's write it down here. Here we have E1. Okay, let's say A1 cosine Z plus B1 sine Z. Okay, and we don't have to solve for E3 because this is the same process for E1 and E3, and you also have K1 times K3. Okay, so even this coefficient is the same for both of them. Okay, if you're not sure, then you can take a derivative for E1 to get your E3. Okay, it's the same thing. Okay. And now we need to use boundary condition. So when you first have the crystal input, we know that E1Z equals 0. It's a number we know, right? You have to know your input. Okay. And then also we know there's no power of E3 at the input. Okay. These are two boundary conditions we know. So using this boundary condition, we know that for E3, it's very clear. As Z equals 0, this term is 0. This one is 1. Okay, so you have A3 equals 0. Okay, and for this one, you have E1 0 equals A1. Okay, so A1 equals E1 0. Now there are still two parameters there, okay? B1 and then B3. And I don't know how much you guys know about wave equations, but usually what happens is that cosine goes with the boundary condition, sine goes with the derivative of your boundary condition, okay? Because you need to have a derivative of sine to go to cosine. Right, and then cosine 0 has a non-zero value. So the way to do it is to use this equation. Okay, we didn't give any. We didn't tell you what is. Right, we never say anything about this. but you can do it from here, right? This equation. We know partial E1 equals to K1 E3. So at 0, z equals 0, this one is 0, right? And what this gives you, partial E1, derivative of E1, cosine goes to sine, so this term is 0. Sine goes to cosine, this term is 1 with a coefficient coming in the front and b1. So when this derivative is 0, it means b1 is 0. Okay. You can go step by step to calculate this. Here I'm just skipping some steps. And now let's go with E3. Okay. This one equals to K3 okay. So this is non-zero. And of course it should be non-zero, otherwise you have maximum E1. So growth rate of E3 must be maximum. Okay. So you can calculate this derivative from here. Again, this one will be 0 at 0 point, right? Cosine goes to sine. And then now you have B3. Okay. This coefficient come out. Cosine 0. Okay. Okay, so this term is 1. So we have B3 equals to K3 and then E1. Okay. So we know what K3 is. We also know what gamma is. Okay. So now let's write it down. Okay. K3 is I. Okay. E2, 0. Okay, this is K3. Okay. And then we had gamma square equals to this, right? So your gamma would be mu naught 0 naught chi 2 omega 1 omega 3. Okay. And then this one is tricky. Okay. This is the amplitude of E2. It's different from E2. Okay. E2 have its amplitude and the phase. And the thing is, you can always choose. Right? We say this before. You can let's see what we choose here. You can always choose a phase, initial phase, of one of them, just one of them, right? Because you have E I omega t plus ikz. Z is, well, you have a 0 point here, so you can't move that. But you can always choose a different time 0, right? So time 0 will give you, can erase the initial phase of one of them. Okay, so I think here we actually go with E1 0 is real. Okay, we choose the time 0 time point to make E1 0 real. Okay, so what I mean is E2 and E3 in general they're a complex number. Okay. Or you can choose E2 to be real, then you don't have to carry a phase. Okay, it's all the same actually. And then now what you get is you have an I here. You cancel all these terms. Okay, you have K1, K3, omega 3, omega 1, the phase of each at 0 point. Okay, E2 divided by its amplitude give its phase, right? And then E1 0. Okay. I think there's a K3, right?
In K3, you're missing the K3.
Yeah. Okay. So K3 come up. Yep. Yeah. And we know K and J, omega J, C, right? So this one goes to I, and you have omega I here, kind of cancel that one, so be N1 omega 3 and 3 omega 1. Okay. So now we can write down the complete solution. E1 Z equals E1 naught cosine. Right, it's oscillating as cosine. This is just what we predict. Okay, there's oscillation there. And E3, okay, there's a phase term. And then okay. Okay, so this is the solution. And then you can see this term. This is this omega 3 divided by omega 1 is kind of like the photon energy ratio, right? The energy per photon. And the reason it has a square root is because this one goes to power, right? So when you square this, you get omega 3 divided by omega 1. Okay, and then let's see, do we have this here? Yes. So let's actually calculate this. Okay. So we know the power of E1 will go like this. Okay. And then P3 will go like this. Okay. So way to check your calculation is to see when you have E1 and E3 is a photon number conserved. It's a photon number. Well, the maximum power here for P3, does it consist of the same amount of photon as your P1 here, right? So to generate each E3, you need one E1, okay? So the way to do this is, let's see, we can write down P3 at its maximum point. Okay, maximum point sign is 1, okay? And divided by, divided by the photon energy. This is the number of photon per second. Okay. Thinking this is the energy per second. So this is the photon number per second. And we know P, the power, its relation with the E is right. This is the expression of this. And you plug in this E3 maximum here, you get A is the cross area of your waveguide. And then you have N3 here. Okay, you plug this in, you have 1 omega 3 and 3 omega 1 divided by h bar omega 3 times E1 squared. All right, you simply plug this in into this power expression. And then you see this 3 cancel out. This omega 3 also cancel out. And you're left with right. So what is this? This is the power of E1, right? The power of E1 divided by the photon energy, the energy per photon in E1. Okay, so what this means is that the number of photon you're able to get here is the same amount of photon you input. Okay, so there's a conservation law here. And so what this also means is that for this some frequency, okay, you're not really using E2 very well, right? If there's a choice, let's see, if there's a choice, you probably would want to suppose this the total energy you input is the same. You probably want to increase E1 a little bit and decrease E2. Okay, and what that would do is that, well, what that would do is this gamma here. I think we erase gamma. Let's write it down. So when you increase E1 and decrease E2 and keep the total energy the same, what will happen is that the maximum amount of P3 you're able to get is larger, right? Because it was capped by the power of your P1. Then what is the penalty? Okay, the penalty is because your E2 is smaller now, so the oscillation takes longer period. You have to use a longer crystal, right? This area, this distance is longer. Okay, so for your system, if you don't mind having a very long structure, then you can think about, having almost equal amount of E1 and E2. Okay, if your system is capped, like your system is only like 1 millimeter long or 100 micro long, you can adjust that. Then you probably having a good E2 is better, right? Because it at least allow like 100% efficiency. Okay, yes.
But didn't we start with the assumption that magnitude of E2 is much larger than?
Yeah. So if your E2 is similar to E1, you have to recalculate everything. But it's kind of like you can imagine that happening. Okay, you can imagine if you give a little bit of energy from E2 to E1, your P3 can go a little bit higher. And of course, that saturate at some point, and then And I think for this type of calculation, maybe Mathematica can already do it for you. So I'm not 100% sure, but you can try. So the sound frequency in optics, it's actually not that widely used. I think in microwave, it's used a lot more. It's called mixer, right? It's not called sound frequency. It's called mixer. And you can actually buy these mixers with plug-in connectors from mini circuits for like $50, and they can work. I think right now they can work to 20 gigahertz, at least for mini circuits. There's some high-end manufacturer probably go to 80 gigahertz or 100 gigahertz and cost you more. Okay, and then for those mixers, one thing you will find is that they require a minimum input power. Okay, minimum input power, probably because if your power is too low, then this distance is very long. Then you're not efficiently using your mixer. Okay, that's my guess. I never really open one, okay, and see what's inside. Okay. And also for the mixer in microwave, you can, they tell you to input. I think most mixers are down mixers. You call. There's a local oscillator. There's I forgot how they call, but let's see. Set this signal. This is idler. Okay. So most of them are down mixers. Let's say you input 10 gigahertz, and then here you input 12 gigahertz, and it gives you 2 gigahertz. Okay. but you can work in a different way. You can rotate them to get you input 10 and 2 and give you 12. Okay, and there's some company, I think they specifically made some frequency because in electronics, in electronics it's difficult to jump from, well, when you jump from 10 gigahertz to 20 gigahertz, the price, it's like, I think for 10 gigahertz synthesizer, the cheapest one I can see, for tunable one is like $1,000. Okay, if you need a fixed frequency, then you can probably get it by $100. But when you go to 20 gigahertz or 40 gigahertz, then it goes to like tens of thousands of dollars. Okay, the one we have, I think the one Andreas Group has called PSG synthesizer. That one, I don't know if any one of you know the price, but that one is close to $50,000. Okay, depending on the options you have. Okay, so the price just keep going up and up. And back in Caltech, when we only have one 40 gigahertz synthesizer, and the other one we have is, and then we have 10 gigahertz fixed synthesizer. So what we do is we don't want to pay money to get the frequency doubler. Okay, so what we do, we play with this, and then very simply configure your cables, and then also you add a little bit distance to match the phase, and then you generate some frequency. Okay, and so that's some frequency. And we can start a little bit about difference frequency generation. So difference frequency generation is much more useful in optics. And at some point I actually thought, some of you can give a lecture here and then waive your final exam, because, for example, for difference frequency generation, you guys are the experts, right? So it's a little weird that I'm talking about difference frequency generation and you guys are sitting there. And I think it might be too trouble for you guys. You probably prefer a final exam. So. And the same apply for electro-optics modulation, and Andreas Group, you guys are expert on this, right? You need to modulate frequencies and then do photodetect. And so if it sounds too trivial to you guys, I apologize. Okay. Difference frequency generation. Okay, so difference frequency generation, we can again plot this energy diagram. You have your atom at ground state, and then you have omega 3, goes to a virtually state, and then you have omega 1. I think it's omega 1. Yes, and these two can do a sum frequency. Generate omega 2. Okay, so we satisfy the energy conservation. And before we write down any equation, I want to think about this question again. Does it keep growing? Assuming your pump E3 is much larger than both E1 and E2. Okay. Any guess? I mean, you guys should be silent. So, okay, other people, any guess? It's a 50-50 shot. It's either oscillation or keep growing. Okay, so.
I think it would oscillate again.
Sorry?
I think it would oscillate again.
You think it's oscillating again? Okay. What about E1? Does it going down? Does it going up? Does it oscillate?
No. No, they can both keep growing if you're assuming that E3 is undepleted.
Yeah. Yeah, that's the beauty of difference frequency generation. That's why it's more widely used than sum frequency. Because this is actually a totally different structure. This is more like an amplifier. And let me show you how this is. So for omega 3, a E3, a photon, every time, this looks a little bit weird, okay? But every time you generate omega 2, a photon omega 2, you have to generate another omega 1. Okay, so role of E1 here is very different from the sum frequency. The sum frequency provides a photon to convert it to omega 2. Here, or to omega 3. Here, this one simply trigger the omega 3 into 2 photons. Okay, it's not consumed. Okay, it stays there. It's more like an optical amplifier, right? We talked about amplifier before. Okay, if you have a photon, electron in upper level, right? The first photon can trigger emission, goes into 2 photons, right? This photon does not disappear. It simply triggers this because of stimulated emission. And then these 2 photons can trigger another electrons to go down. And then you get amplified. Okay. So here is something actually similar, right? You have, well, we have to draw it a little differently because there's a very different process. There's a distinct difference between these 2 processes, although they are all amplification. So let's see, we have a lot of photons in omega 3, right? And then, where's my note? Okay. And then they're propagating along this waveguide. Okay, and then now you have a photon coming in at omega 1. So what this can do, this can trigger 1 photon in omega 3 into 1 photon of omega 1 and 1 photon of omega 2, right? And then the original photon stay there, okay? And then it can keep doing this. I'll just say minus a photon, okay? And then now, if you keep doing that, they're co-propagating. Okay, you now minus 2 photons in omega 3, and then you generate. Right? Yes?
So you need one initial photon at omega 1 to get out.
Not necessarily if you're in a cavity, because there is a vacuum fluctuation.
Okay.
So you don't always need it. Okay.
And how do you control what the omega 1 and omega 2 are?
You do phase matching. Okay, so it's a little bit.
Okay, so you constrain what they can do.
Yeah, yeah. So if it's just a waveguide, then again it's phase matching. Okay, whatever phase match, you can generate a little bit of that. So just as what you said, if there's no photon there, there'll be half a photon on each mode, actually. So in this semi-classical picture, you might get zero result. Like if you have zero input in E1, then you have no output. Okay, but if you do a quantum calculation, okay, I have never done that, but I believe you'll have some output, and I think it's called spontaneous emission, right? Okay. And they're entangled, right? If you do spontaneous, okay. So the critical difference between these two processes, okay, is that you can actually see from this diagram. Compare these two. Okay. So for this one, it's like a very normal amplifier. Once you amplify these photons, the electron coming from will go from upper state to lower state, right? And then you need another pump to pump it back. So the state of your material before amplification and after amplification is different. Okay. So like in here, you have all the after you generate this. Okay. And for this one, you actually start from here, ground state, to a virtual upper state, and then going back to a ground state. So your material stay all the way in the ground state. Okay. So there's no change in your material. And that's actually, it doesn't sound like a big deal, but if you think about it, it actually is, because first of all, you don't need a real atomic state or semiconductor state to help you to do this. Okay. And for example, for fiber amplifier, because we need to dope erbium. Okay. So you're limited at, there's a CL band. It's roughly 50-30 to, I think there's different definition, but roughly this wavelength. But for this amplifier, you don't have that constraint, right? Because this is a virtual state, so it can do a much broadband amplification. Okay? That's one thing. The second thing is there's a relaxation time, okay, from here to here, and then you repump it to the upper state. So your material actually, there's some property in your material that might stop you from doing what you want. Okay, for example, fiber amplifier and semiconductor amplifier, they behave quite differently. Okay? And so for example, if you want to amplify pulse, okay, a very short pulse, I think people normally use this amplifier. And then starting and some people, like in our group, we use fiber amplifier because of, it's easier to buy. But almost always there's nobody use semiconductor amplifier. Okay, part of the reason is that if you put a lot of photon in there, and there's a very complicated interaction between your light and the semiconductor, that actually mess up the phase of your light. So it's not always like you have a phase. It's not always like these are all the same phase. Okay, so so this parametric, this is called parametric because the material stays the same. It just changes state from upper to lower, lower to upper. So this is called parametric process. Okay. If you make it to an amplifier, it's called parametric amplifier, right? And we know before, if you have amplifier and you add a pair of mirror, right? Bounce the photon back, keep triggering the emission, it becomes a laser. Right, so the same thing can happen for this parametric process, but it's not called parametric laser, it's called parametric oscillator. Okay, oscillator is same thing as laser in many cases. So this part, amplifier and mirror, become parametric oscillator, and then there's a special name for it. It's called OPO, okay? Optical parametric oscillator. And then it's really widely used. Okay. If you guys want to waive the final exam, you can think about give a talk on how to do a quantum picture of this parametric amplifier or oscillator. And I think the key is to illustrate the idea of how to create entanglement and squeezing. Well, you can think about it, and then we can discuss. And then also, I want to be fair to all other students, right? So if we reach a level that I think it's, if you can give a talk like this, you must have no problem with the final exam. Then we can proceed with this. Okay. If it's too general, then probably no. Okay. Yeah. So think about it. Okay. And for the rest of you guys, if you happen to know something in the list that you think, well, I know much better than you, right? Much better than me, then you can propose something we can discuss. And then, you have no idea how much I want you guys to do this, because I have to finish 3 proposals in the next week, and then our lab is moving in with optical tables, and then just save a lot of time for me, and then also having a real expert talking about this optical process here. Okay. Oh yeah, by the way, I want to ask, if there's a quantum mechanics class next semester, how many of you will register? Will feel like to register? Okay. Good. Beijing, you should not register. The one you took at undergrad is much difficult than the one I want to give. Yeah, it's just I have a quantum mechanics class next semester for undergrad, and then it's about 9 students register. I think maybe I have to discuss with someone to see if we can expand it to a joint class. Yeah, but the thing is, they always want me to justify, justify for the graduate student, the class would be more difficult than the undergrad. And it's, well, the thing is, well, it's one thing that I write a justification, but it's the other thing that they actually buy it, right? Like, how is that even possible? It's the same classroom and I teach the same thing. How is that even possible that the graduate level is more difficult than undergrad level? Unless I give more homework, but then it also doesn't make sense, right? Why would you torture your graduate student? So, but I think it's just a paperwork that, I think everyone knows what's happening, but they just need the paperwork. And yeah, luckily, like for this class, there's no undergrad, so otherwise you guys will all have to do some homework to show that there's a difference between undergrad and grad student. Okay. Now let's write down the equation for this, and we can stop here for today. Okay. So again, there's 3 waves. Okay. So we can skip all the middle part. You can look at it as a note. Okay. We always have this divided by K1, right? And then to generate a E1, the process is a E3 to E1 and E2, right? So usually this type of process, you simply write down E1, E3. E1 is already here, so you write down a E3. Okay. Now how about E2? E2 is normally on this side. Okay. So when you move it from this side to this side, you add a conjugate. Okay. So in quantum mechanics, quantum picture would be very clear, right? One is creation, one is annihilation. Right, so you annihilate a E3 to generate E1 and E2. Okay, so E3 and E2, they must be off by a conjugate. And then you have the phase matching. Okay. And similarly, G2. Okay. So let's see a critical difference. Well, first of all, this equation looks identical to the one of some frequency, right? If you check the note. Okay, because it's still this 3 wave. Okay. It used to be omega 1, omega 2, generate omega 3. It just reverse. So, but then we know that there's this very, very different behavior. So in a mathematical way, where does that come from? Okay. Where can it come from? So previously, let's make a quick comparison here. So previously, I think we solve E1 and E3, right? And then we take E2 as a constant. So you see this is keep the I here, okay? This is for some frequency. Okay, for difference frequency. And of course, again, we assume the pump is very strong. The pump this time is omega 3. So we need to solve E1 and E2. All right, so you have I. This is just a coefficient now. We'll go in detail, in the next class. I just want to show you why there's a difference in its behavior, okay? And I, E2, this is coefficient, E1 star. Okay. So see these two equations, they have the same form, but you're off by a conjugate. You're off by a conjugate. And we already talked about conjugate and no conjugate means you're either creation or annihilation. Okay? So this one is whether you take the photon or you create a photon. So that's the difference. Okay? Mathematically, there's a difference. Then when you do the calculation, again, we take derivative, right? We take derivative of this, and then we plug this in. And then we get I plus I, we get minus 1. Right? We get minus 1 E1. Right? We get a minus sign here. You get oscillation. Here, you do the same thing. But notice now, you cannot plug in E2 directly. There is a conjugate. So you have to take conjugate of this equation and then plug it in. Right? This one becomes right. So you need to take conjugate of this, plug it into here. So when you take conjugate, there's an I become minus 1. Okay? So this I times minus I E1. And this one becomes plus. Okay? There's a minus sign here. There's no minus sign here. And then for minus sign, we know it's sine and cosine, right? For this, for this, we know the solution is it's exponential growth or decay. Okay, so I hope you guys kind of can understand this, and then really in your own research, when you see a process, you're able to predict some behavior, and then save you some time. Like if you want to build an amplifier. Right? If you want to know if the process can be made into amplifier, you really don't need to calculate everything. You can, check all this and then get the result. Okay, that's all for today. Thank you.